Hello, everybody. Thank you for joining us today. You are part of the 200 people worldwide who registered to watch this webcast, powered by Yole Développement, System Plus Consulting, and KnowMade. The webcast is entitled Power Silicon Carbide Adoption. What will be the next steps? My name is David Jordan, and I am Global Sales Support and Coordination Manager for Yole Développement. I will present this webcast. So before we get started with the webcast, let me give you some basic information on this online event. You have the possibility during the webcast to submit questions. To do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions as time permits today at the end of the webcast. And for the remaining questions, we will follow up with you via email. Concerning the materials presented during the webcast, please note that the presentations are already available and downloadable in the resources section of the platform. Furthermore, within 24 hours, you will receive an email with a link to the recorded webcast session. So let's start the webcast with Hong Lin, Principal Analyst, Compound Semiconductors from the Power and Wireless Division of Yole Développement. Hong, the floor is yours.
Hi, David. Thank you for introduction. So hi, everyone. So I'm Principal Analyst at Yole Développement in charge of compound semiconductor activities. So today it's my pleasure to share our understanding of silicon carbide power device market. So just before going to the Can-10 and the topic of today, I just would like to shortly introduce Yole. So Yole is a group of six companies: Yole Développement, System Plus, KnowMade, PZO, Group Morpho, and Yole Finance. I'm working at Yole Développement. It's a market, technology, and strategy consulting company. And at Yole Développement, we cover a wide range of semiconductor applications, such as imaging, MEMS, RF devices, to packaging manufacturing. And today's talk is about compound semiconductors and power electronics. So, we are doing market forecast. So before we talking about a number, it would be nice to have an idea about our methodology. So to achieve market estimations, you'll use two approaches, the top-down and bottom-up approaches. So in the top-down approaches, we were looking from the system, for example, the number of cars, how many inverters inside, how many devices in the inverter or converters, and then we calculate wafer. We will also have a bottom-up approach where we'll discuss with wafer or AP wafer suppliers about the wafer shipments and to consolidate our data. We also have discussion with all the players involving in the supply chain in order to have a better overview of the market. So now we were directly looking at the power electronic market before going to silicon carbide in more details. To looking at the overall power electronic market, 2017 was a very good year, and 2018 was even better with increase by almost 14%, and the overall power device market reached 17.5 billion, including both silicon carbide and gallium nitride. The power IC are not included here, and Yole will release a dedicated report to power IC in Q4 this year. So in 2019, the year began on a very positive note, but the demand is dropping because the major customers still have a lot of inventories last year. And we are also expecting a market slowdown in 2020 as MOSFET prices has reached its maximum. And device manufacturers expect the MOSFET price to drop in the following quarters. So, but if we look further, we are still expect the market demand to keep growing, mainly driving by electrical vehicle market. And so the markets we are expect to reach more than 21 billion in 2024 with a compound annual growth rate of 3.2%. So for those who don't know very well about power electronic applications, just a very short introduction. Here on the slide, you're looking at the vertical axis that's about the power range, and on the horizontal axis, the frequency range. We see different applications positioning at different power and frequency range, and almost still today, silicon devices is still everywhere. We have series at low frequency range and MOSFET at high frequency range. So as the silicon devices approach its limits, we hear more and more talking about the silicon carbide or gallium nitride devices, where silicon carbide is more for high power applications and GaN is more for the high frequency applications. So we have seen before that the total power device market is about 17.5 billion. So the question is, what's the share of silicon carbide power device today? So on this slide, we are looking at GaN and silicon carbide device market share. So we see in 2018, the market share of silicon carbide is still very small, only about 3%. But if we're looking forward, we see the market share of silicon carbide is growing very fast. And as silicon is growing single digit, silicon carbide is expected to have a double-digit growth, and we are expecting this share to approach 10% in 5 years' time. So in the following, we will have focus on the silicon carbide power device market. So as you can see on the figure in front of you, in 2018, the total silicon carbide power device market is estimated to 420 million. Among all the applications, PFC and power supply applications are still leading the market, as it has been in the early days of silicon carbide technology. This application drives a huge volume of diodes and some MOSFET application. PV used to be the second largest market for silicon carbide devices in our estimation, but in 2018, it is down to the third place taken by automotive market, which I will talk later. So when we're looking at the PV market, the market is growing very well. There are more and more installations worldwide, despite the suspension policy change in China. The rest of the world is taking off, and the PV market is growing. But there is very high cost pressure, and the silicon carbide adoption is not growing as fast as we expected in 2018. But on the other hand, we see the new trends in the PV segments. We see nowadays these PVs are more and more connected with energy storage system using a DC-DC converters, which connecting the battery storage to the PV array. And silicon carbide really brings added value here by increasing the efficiency. So the combined market is expected to grow to more than 230 million in 5 years' time. So now, looking at the automotive market is the yellow part that you see on the figures, and the EV market is the primary driver for power electronic devices in general, and it's the same for silicon carbide. So due to the strong CO2 emission targets worldwide, there is a global trend toward more and more electrification of the vehicles. So more than 300 billion investment has been done by OEMs to electrify their cars. And with more and more of prototyping and demonstrator, there is no doubt today there is real added value for silicon carbide in different applications for automotive. So we believe that silicon carbide is already widely used in onboard chargers and will be widely adopted by onboard charger applications in the coming years. And in 2018, Tesla has adopted the silicon carbide in many inverters, and this has created a very big excitement in the silicon carbide power industry. And we are expecting the more companies to adopt silicon carbide in the coming years. In particular, we believe BYD will release a silicon carbide-based inverter in small numbers at the end of this year, and other OEMs will follow. So the total automotive market is expected to approach 1 billion in 2024, representing about 50% of the market. And so apart from the EV market itself, together with the booming of the EV market, charging infrastructure is emerging as a very attractive market for silicon carbide. So we see a lot of charging stations being rapidly deployed in Europe, in US, and in Japan, and in particular, very impressive deployment in China. And so charging infrastructure is also expected to be a very strong driver for silicon devices in the coming years. So in this slide, I just would like to share a comparison of Yole's previous data. So we see from 2018 to 2017, we have increased our forecast due to a higher implementation of silicon carbide in the automotive market, in particular the adoption of silicon carbide by Tesla. If we compare to 2019 to 2018, our global forecast trend is not really changed too much, but we have adjusted the forecast for different segments. In particular, we are increasing the automotive forecast, but lower the forecast for some other industrial segments. So that's the global market. Here, just to looking about the different device type. So we know there are two types of device, diode and transistor that are using based on silicon carbide. And here you see a figure that breaks down the bell die revenue by diode and transistor. So several years ago, a diode was the majority of the market. And in fact, in 2019, we have identified up to 22 diode suppliers. But on the other hand, the market share of transistor is growing very, very fast. So from less than 20%, like 2 or 3 years ago, to nowadays 40%. If we estimate at a bell die revenue level, and if we're looking at the packaging level, the transistor share is even higher, is approaching 50%. And we were looking forward, we expect the market share of transistor continue to growing and become the majority of the market. So finally, just to have the ranking of power device manufacturers. So the top 5 manufacturers is not changed, but in 2018, thanks to the deal between ST and Tesla, ST has managed to overtake the #1 place from Wolfspeed for the first time. And so the first 5 players is ST, followed by Wolfspeed, ROHM, Infineon, and Mitsubishi. And we also see that on semiconductors has a revenue that progressed very quickly since they introduced silicon carbide products. So to conclude for today, silicon carbide power device market is expected to grow very fast, driven mainly by automotive markets in the coming years. The market potential is really very huge and attracts a lot of players, and we expect the competition to be very strong in the coming years. So this is my talk, and if you have any questions, we can exchange later.
Thank you very much, Hong, for this very nice presentation on power SiC. We will now continue with Amin Alouche, Junior Costing Analyst at System Plus Consulting. Amin, it's your turn.
Thank you, David. Welcome to all the listeners to this webcast about power silicon carbide adoption. So my name is Amin Alouche. I'm a Junior Costing Analyst at System Plus Consulting, and I will be giving you an overview about technology and cost of silicon carbide power MOSFETs. So a brief presentation of System Plus Consulting. We are a French company, part of the Yole group of companies. We specialize in reverse costing. That means reverse engineering in order to calculate the fabrication cost of different devices and systems and all the application fields you see in this slide. So for today, I will present the different technologies of silicon carbide MOSFETs that we have analyzed so far at System Plus Consulting. I will illustrate this with some costing aspects, and finally I will conclude my presentation by giving some technology and cost comparisons. So this introductory slide, in fact, is to show you the available silicon carbide transistors in the market. It plots the voltage versus drain to source current. What you can notice is that the majority of these devices from different manufacturers, ST Microelectronics, Wolfspeed, RAM Semiconductor, etc., have a breakdown voltage of 1.2 kV, which is until now the most attractive voltage class in silicon carbide MOSFET market. This comparative graph shows the difference in current densities offered by silicon carbide MOSFETs versus silicon IGBTs. We clearly see here two separated regions proving the interesting performances of silicon carbide MOSFETs that are offering superior current densities over their silicon counterparts. Now let's have a look on the device's technology. Two main design solutions for silicon carbide MOSFETs currently exist on the market: planar versus trench gate structure. Each one has its own advantages, of course. For example, although the planar process is less complex in fabrication, trench allows to reach better electrical and physical performances, loss reduction, die size shrinking, etc. This slide is summarizing, in fact, all the technologies that we have analyzed in our laboratory at System Plus Consulting. Different planar and trench structures were identified for various manufacturers. Some of them propose two types of structures, such as RAM Semiconductor with its planar and trench structure. Others still maintain their planar structure for all the three generations, like Wolfspeed, and others specialize in one device type, planar, for example, for ST, and Littelfuse, and trench for Infineon. We try to sketch here the performances of our analyzed devices. Two parameters are useful for this evaluation: the charge times the drain to source resistance, and the specific resistance, which is the area times the drain to source resistance. So this graph shows first the evolution of the figure of merit, LDS1 times QG. What you can see is an important evolution over the past years for all manufacturers, and especially when it comes to the trench devices that are showing really best performances and the best figure of merit in this case. Another figure of merit, as I said, is the specific resistance, and again, trench devices seems to be the best for this figure of merit as well, although some planar structures are doing good performances and even approaching trench like Wolfspeed for its second generation. In this slide, we show you the main four technical challenges that silicon carbide devices are facing. First challenge is the silicon carbide wafer processing and reliability when transitioning from 4 to 6 inch wafer diameter. The second challenge is the gate design, planar versus trench, as I previously explained. The third challenge is the processing. Some front-end steps remain challenging for silicon carbide wafer, like epitaxy, gate oxide entrance structure, as you see here in the Infineon device. And finally, you can mention the packaging. So now let's give some costing aspects about silicon carbide MOSFETs. And I will start by giving the main cost drivers. So silicon carbide wafer remains, as you may understood, a major cost factor for silicon carbide devices. In the graph, you see that despite the higher wafer cost of 6-inch silicon carbide, the transition from 4-inch to 6-inch would permit to reduce the cost per device, since a larger wafer permits to have bigger number of dies per wafer. Again, despite this advantage, we need to bear in mind the challenging aspects, of course, related to this transition. Another cost driver for silicon carbide processing is the epitaxy, which is confirmed by this cost chart that compares the front-end steps cost breakdown in a silicon carbide MOSFET process. I will conclude my presentation with some comparisons of selected silicon carbide MOSFET manufacturers. And I will start by Wolfspeed. So Wolfspeed is continuously improving its device's performances regarding the different figure of merits when moving from its first to third planar generation, as well the device cost per current, which what we call the ampere cost here in the table. We calculated it is showing really great performance and improvements. In this slide, we show some data related to RAM semiconductor, planar generation 2 and trench generation 3. For the same voltage, trench design is more performant, but regarding the complexity of the process, its wafer cost is higher, as you may see. However, taking advantage from pitch reduction of the trench structure, potentially the higher number of dies, the final die cost is less expensive than the planar die, which is a big advantage for trench devices. This final slide is to show the costing advantage of silicon carbide devices. By comparing the die ampere cost of our analyzed silicon IGBT and silicon carbide MOSFET for two voltage classes, 650 volts in orange and 1.2 kV in blue. And the conclusion is that the silicon carbide MOSFET dies still have higher cost than silicon IGBTs in order to offer all the performances that we have presented in the previous slides. To conclude, silicon carbide MOSFETs are still young devices with promising technology that still need to face some challenges in the near future. And for further information about technology and cost, you can check our newest report at System Plus Consulting about silicon carbide MOSFET comparison in 2019. Thank you for your attention.
Thank you very much, Amin. Just before the next presenter, let me remind you that you can ask questions using the Q&A button so we can answer some questions at the end of the webcast. So the next person to present is Rémi Comin, Patent and Technology Analyst at KnowMade. He will conclude this webcast. It's your turn, Rémi.
Thank you, David. Good afternoon, everybody. I'm Rémi Comin, Patent and Technology Analyst at KnowMade, and today I will give you an insight of who are the main players in the patent landscape related to power silicon carbide technology, and also we comment about what is their profile. So we're going to talk a little bit about history of IP players and dynamics of their patenting activity. So here, basically, we have a list of the main patent applicants in the silicon carbide power MOSFET patent landscape. So it's a ranking. And in this ranking, we are going to see some players which are not already in the market, but have a large patent portfolio, such as Denso, Toyota Motor, or General Electric. We are going to see also most of the market leaders, such as Wolfspeed, Infineon, from semiconductors, and also interesting some of their IP, some of their market challengers, such as Mitsubishi Electric and Fuji Electric, which actually has the second patent portfolio on silicon carbide power MOSFET. So what could be more surprising is the position of important market players such as ST Microelectronics and ON Semiconductor, which seem to have a small patent portfolio related to silicon carbide power MOSFET. But this doesn't mean that they don't have a lot of IP applicable to this technology. It just means that they have a limited number of patents which explicitly mentions silicon carbide power MOSFET technology, either in the claims or in the embodiments of their invention. So instead, they may have filed generic patents, which patents that does not mention the target material, or another possibilities, also transfers of technology. So transferring technology from previous patents, for example, from silicon-based power technology to silicon carbide power MOSFET technology in that case. So going into more details, with the analysis of patent portfolios, we can reveal on which technology IP players have been focusing. So this in turn can tell us about strategy of players. So, for example, what are their business opportunities? What is considered as critical for market acceptance? For some players, it's pretty obvious that they are focusing on the trench MOSFET technologies, such as Fuji Electric, Denso, Infineon, Toyota Motors. While for others, they're clearly focusing on planar MOSFET technology, such as, for example, General Electric, Wolfspeed, Mitsubishi Electric, and for some other players, it's less clear if they are focusing on one or the other technology. And this is the case, for example, for Sumitomo Electric. Now a word about history of patent filing. So this is a timeline for patent applicants. And in these timelines, we have identified 3 different groups. So the first one is established IP players, which are called this way because they are long-standing IP players in this patent landscape. So, but in this group, we have different profiles, kind of profiles. For example, General Electric, which is indeed long-standing IP players in the field, but has not been very active in the past, and has become active more recently. So now it's the most active patent applicant actually for the silicon carbide planar MOSFET technology. Different case is also is Wolfspeed, which have a long history of patent filing in silicon carbide MOSFET technology patent landscape. But we noticed that Wolfspeed have clearly slowed down its patenting activity on silicon carbide MOSFET around 2015. Actually, we think that it's because it has built, according to our analysis, the strongest IP portfolio, and it does not need to reinforce its IP position any further. Another case is Denso, which similarly to Wolfspeed, according to our analysis, has built the strongest IP portfolio for trench MOSFET technology. And but it's still very active in terms of filing patents. So still strengthening its IP position. So the second group of players that we have identified is composed of players arrived later in the patent landscape, and which have been trying to catch up with established IP players. So they are clearly challenging them. And examples of such players are, for example, ROM Semiconductor and Sumitomo Electric and ST Microelectronics. And the last group we have identified are new entrants. And here we see that we have mostly Chinese industrial player, which is an important change in the patent landscape, because since 2010, the presence of China in silicon carbide MOSFET patent landscape was limited to academic players such as Zhejiang University, USTC, and another noticeable entry in the patent landscape is SiC Power, which is, to our knowledge, the first industrial player from Taiwan, despite the presence of a long-standing academic player with high TR. Now let's move to the second part of my talk. So here, basically, we have an evolution of patent publication over the years. Patent publication related to silicon carbide power modules. So what we see is that until 2009, the patent publication rate was quite limited, and we think that's because at first many players have tried to transfer their technology developed for example, silicon IGBT power modules to silicon carbide power technology. Then we've seen some players developing specific power modules for hybrid modules, so modules combining, for example, a silicon IGBT with silicon carbide diode. And from 2011, 2012, we've seen that more and more players are developing specific power modules specific to silicon carbide technology. So this is illustrated by the increase of patent publication dedicated to focusing on full silicon carbide power modules. So again, we have a timeline of patent filing. So basically, it's the mosaic of the main IP players which are present in this patent landscape. Again, we have identified established IP players. The largest IP portfolio for silicon carbide power modules are held by Hitachi and Mitsubishi Electric. But what's interesting here is that we see several important IP players from the silicon carbide power MOSFET patent landscape, which are now focusing their patenting activity on silicon carbide power modules. So this is particularly the case of ROM Semiconductor, which is the most active patent applicant in this patent landscape. And this is also the case of an established IP players, which is Pre-Wolfspeed. We've seen that it has slowed down its patenting activity on silicon carbide power MOSFET around 2015. And in contrast, it has accelerated patenting activity on silicon carbide power modules still around 2015, which is also concomitant to the acquisition of Arkansas Power Electronic International by Cree at the same time. So, and now Cree Fayetteville. In the new entrant, we have several Chinese industrial players as well, such as State Grid Corporation of China. We have also the entry of Danfoss from Germany. This is interesting. It's not a surprise. It's confirming the interest of Danfoss for silicon carbide power technology. And what's also is interesting here is to highlight the link, the connection with General Electric, which is, as mentioned before, one of the most active patent applicant for planar MOSFET, silicon carbide planar MOSFET technology at the moment. So this is the end of my talk. I want to thank you for attending, and do not hesitate to send me your questions.
Thank you, Remy. So thank you all for your presentation. We are now ending the webcast, and we will conclude with the Q&A session. We have many questions. We will try to answer all, and we will follow up with you via email later on. So the first questions are for Hong Lin from Yole Développement. What is the status of the silicon carbide wafer supply?
For the silicon carbide wafer supply, we know that since 2016, there are wafer short supplies, and the situation was still very tight since the early 2019. I think the situation is much better since at the end of Q2 2019, as all the major players began to extend their wafer capacity. We are seeing the offer and the demand begins to change, and the wafer price is dropping again. So what I can say is the wafer supply is in a better situation, and we have seen very impressive announcements from different wafer suppliers. So I'm hoping the supply will continue to grow.
Thank you. Our last question for you. How do you see the silicon carbide module market?
So as of today, actually silicon carbide is positioning for the same application as IGBTs, and so module is expected to be the most important thing in the future in our understanding. As of today, there are began to have initial module offers. We still see different challenges for silicon carbide module packaging. I would like to say silicon carbide module is still in the early development status today, but we are expecting this market to grow very fast in the coming years.
Thank you. We now have a question for Remy from KnowMade. So according to market analysis, automotive is already the main driver for silicon carbide power technology. Can you comment what you see from your side? I mean, the patent landscape.
Yes, it's an interesting question. I think the best way to answer this question could be by looking who is in the automotive market, who has been active recently in the silicon carbide power patent landscape. So let me come back to this graph. So for example, for the silicon carbide power MOSFET patent landscape, we see that the largest, so the answer is pretty obvious, the largest patent portfolio is held by an established automotive player, Denso. And what also is interesting here, I think, it's that Denso has an intensive IP collaboration with Toyota Motor and Toyota Central Lab. So, and this we have seen this since 2012, and just for silicon carbide power MOSFET, I think it's more than 40 patents that have been filed between Denso and Toyota Motor. Just for silicon carbide power MOSFET, we also seen some strong patent activity on the silicon carbide Schottky diode from Toyota Motors, and also for silicon carbide power modules more recently with actually a collaboration between Toyota Motor and Virginia Tech and silicon carbide power modules. And I think it's not the only player, automotive player, active in this patent landscape, because I also see Hyundai Motor, which has been developing trench MOSFET technology since 2013. And yes, all these players, Hyundai Motor, Toyota Motor, Denso, they are focusing on the trench MOSFET technology. So I think this is clearly confirming the interest of automotive players for the silicon carbide power technology.
Thank you, Remy. Now we'll follow up with Amin. We have one question, well, two questions in fact, regarding the better performance of trench devices. Can you comment why some manufacturers continue with planar design?
I see. In fact, as I mentioned in my presentation, some designers like Cree Wolfspeed are offering planar silicon carbide MOSFETs for all their generation, and this brings us back to the technological challenges that trench designs may face. For example, the complex fabrication process or the reliability of gate oxide, and this may hinder, in my opinion, the trench design adoption for some manufacturers.
Okay, last question for you. Why silicon carbide epitaxy has an important impact on the final wafer cost?
Yes, so this brings us back to the costing aspects that I presented. So indeed, the epitaxy is a cost driver for silicon carbide devices, and in my opinion, this is linked to the complexity of the manufacturing step, including, for example, silicon carbide wafer preparation before the epitaxial growth. And for information, the wafer is engaged in a temperature cycle from room temperature to high temperature, nearly 1,600 degrees Celsius, and this impacts the throughput of the operation, and hence it will impact the cost, since it is a time-consuming step. So this really justifies the important impact on the wafer cost.
Thank you very much, Amin. We have one last question for Honglin. When do you expect 200 millimeter SiC wafers to go in production?
So in our understanding, we don't expect the 8-inch wafers, the 200 millimeter wafers, to come in the next 2 or 3 years, but more in 4 to 5 years time. But if we're looking at how the silicon carbide wafers developed in the passing years, so it has been quite almost 10 years between 4-inch and 6-inch, and each time before the demonstration. So we know the 8-inch was demonstrated, I think, first by 26 and then by Cree in 2016, around 2016. So I think since the first demonstration to when it go to the market, there's still any technology development. And the second thing is also need the market volume to go to some range to justify the transition. And so that's my answer to the question. I just want to say that I will be in Ice Cream Conference, the Silicon Carbide Conference in Kyoto at the end of September to the to 4th October. So if you want to meet me to have a face-to-face meeting, don't hesitate to send me an email.
Okay, thank you very much, Hong. So the webcast is now ending. You will soon receive the link to the recorded session of this webcast. Feel free also to share the presentation with who will benefit from our data and analysis. And finally, also let me remind you that you can find all our market research on our website, i-micronews.com. Do not hesitate to contact us if you have additional questions. You can find the appropriate contact information on the last slide of the presentation. Thank you all for joining us today. Thank you for the presentation, and have a good day. Bye-bye.